on this marker less. So barium carbonate has a measured solubility of 4.03 times 10 to the minus 5 at 25 degrees. Determine the KSP. Okay, so if we're talking about solubility, we have to know what that means in terms of a balanced equation. So first, we have to write the equation. Barium and carbonate. Right, is that correct? Barium is an alkaline earth, so it's +2. Carbonate's polyatomic ion is -2, so that's balanced. This is a solid. So we're going to put it in solution, limited as it is. What does it produce? It produces a barium and a carbonate. Okay, there's a balanced equation. The solubility. So it's solubility, and we'll call that, I'll tell you what. Let me put it down here because I need that space. Solubility is 4.03 times 10 to the minus 5. What does that mean? That means that this is molar. So that's that many moles per liter of this compound going into solution. That's what that means. So in terms of ions, if 1 mole of this goes into solution, how many bariums go into solution? 1 of those and 1 of those. Okay. All right, so let's equilibrium constant, KSP. KSP is going to be, it's already going. Have a spare in my pocket. Wrong color. KSP expression would be barium times carbonate. No powers? Well, 1 power. 1 power, 1 power. This one is not part of the expression because it's a solid. I mean, a good test of whether I can. Okay. So if we use our ice table for number 5, this is probably overkill, but the solubility being this value, then initially, of course, we're going to say that there's nothing there, and then the change is going to be plus 1 of these because it's 1 for every 1. And then, of course, you're going to have this will enter into the equation. So since they're the same value, we've actually got 4.03 times 10 to the minus 5 squared. I get 1.62 times 10 to the minus 9. Which is E. So a pattern should be developing. When you have solubility. Solubility in terms of the solid translates into something for these values over here. And all you need to know, no matter what the coefficient of the solid is, if there is one, you need to focus on what does that mean in terms of the soluble ions. So let's say the mathematical expression for finding the molar solubility of SnOH2. All right, so this is going to be a solid, and it's going to make what? It's going to make this one and this one. Aqueous. Okay. The molar solubility would be a value here. So what is it going to make over here? One of these goes into solution. One of those is going to end up over there. And two of these. So if one of those goes into solution, you're going to get two of those and one of those. And then the expression for KSP is simply this one times that one. That's to the first power. And this is to the second power because of that coefficient. So when we resolve all of that, 2 squared is 4. And then this is squared, and that's the first power, so it's S cubed. Okay? And that should be D. So this time I did it without the ice table, because the ice table is really overkill when you're talking about solubilities. The first one we worked from solubility to KSP, and from this one we worked from KSP. We did actual values of solubility and found the KSP. This one is theoretical. You could plug any number solubility in here. But if you know what the KSP is, now you can find out what the solubility is, because you know the expression in terms of the solubility. So all we need is the KSP for stannous hydroxide, N2 hydroxide. Okay? That's sort of a circular nod.
So
You want to look up another one and see if that has this form. Let's see. How about, there should be a bunch of them. Or you just make something up.
is 8 not one of the same?
8. Well, it's a real value. I was thinking in terms of these placeholders. Yeah. So let's make up about this one. Okay, I'm going to say this one is a 2+ charge. This one's 3- charge, right? So to balance it, we need 3 over here and 2 over there. Okay, so that's our solid. And we're going to have this one go into solution with a 2+ charge. There'll be 3 of them. This one is going to have 2 phosphates go into solution. Okay. Now, if its solubility is in terms of S, so many moles of this per liter go into solution. What do we have over here? Well, for every one of those, you have 3 of these, correct? Did I lose you somewhere?
No,
Processing.
Yeah.
Okay. And then for every one of these, we have two of these. Okay. So our KSP is going to be this one to the third power. And this one to the second power. Okay. So 3 times 3 times 3 is 27. S cubed. Okay. And this one is 4 S squared, which would be, we have S to the 5th power. Add the exponents. Yeah, that's right. Then 4 times this one would be 28, and 2 plus 8 is 10. 108 S to the 5th power.
that makes sense.
I want to pick a really hairy one just so we have an opportunity to scare up the demons. Okay. This one may be in there somewhere. I just couldn't find it really quick. And that was not working either. Let's dig into my stash. Okay. Let's take a look at number 11. Here it is. Which of the following compounds has the lowest solubility in moles per liter, molarity? All right. We got what? A through E. Our compounds are silver phosphate, tin, hydroxide, we did that one already, cadmium, sulfide, and calcium sulfate, and aluminum hydroxide. Okay. If the compounds produce the same number of ions, then you can do a direct comparison with the KSPs. But if they have different numbers of ions produced in the process of dissolution, then you have to actually calculate their solubilities. Okay, and I think that's the case here. We got 3 plus 1 is 4, 3, 2, 2, and 4. So we got to calculate the solubilities for each one of these. All right, we need a pattern so we can channel Henry Ford. So our pattern would be, let's just take this first one. And we have 3 silvers plus 1 phosphate. So the KSP, if we make S common to each one of them, because that's what we're aiming for, right? Solubilities. Make S common to one of them, but in terms of solubilities, this would be 3S and this would be S, correct? Right. So what would this one be? That would be an S for 10 and 2 S's for the next term, right? These are not the same as that. They're based on this right here. This one would be an S and an S. 1, 1. This one would be an S and an S. And this one would be an S for aluminum, and 3S for hydroxide. Okay, so now we have a pattern. We don't need this part anymore. Okay, so if we write 3S, S. Okay, so now if we write the equivalent equilibrium expression for each one of these, then this is going to be 3S, but it's also going to be cubed. And this will be to the first power, because there are three of them. That's the coefficient. This is in terms of the solubility, but that's the coefficient. So this one's going to have a 2 here and a 1 there. This one's going to be singles, singles. This one's going to have 3 of these, 3 OHs on that side. So that means, okay. So there's our pattern. And each one of these has its own KSPs. Right. First one is 1.8 times 10 to the minus 18. Second one is 3 times 10 to the minus 27. Cadmium sulfide is 1 times 10 to the minus 28. See that. Calcium sulfate is 6.1 times 10 to the minus 5. And the last one, 2 times 10 to the minus 3. Okay, so now we've got our equations in terms of solubility. We just have to solve each one for S. Okay. Let's see. Let's do this. This is going to be 27 S cubed plus 1 S to the 4th. Okay. Good so far? Okay. This one's just going to be S squared. This one's going to be S squared. This one's going to be 4S squared plus 1 is 3. 4S to the 3rd. Okay, I squared 4, squared S, and then 1 more S makes 3rd. This one is same as that one. Okay. So now all we have to do is resolve. We have, for this one, we have to divide by 27 and take the 4th root of it. Okay. So you have to know how to do those roots in your computer, in your calculator. That's the one thing about RPMs. They don't have multiple root keys. You have to interpret. So let's see. I don't want to erase that. We've got these resolved, so let me do this. Next space. There we go. So now, let's do the simplest ones first. Take the square root of this. 1 times 10 minus 20. I do have a square root. 1 times 10 minus 14. Right, that should have been obvious. And this one, and now it's 6.1, so I can't do the quickie for that. Exponent. It's 5, and take square root of that. 7.8 times 10 to the minus 3. And next easiest one. Take this one and divide it by 4. okay? And then take the third root. So in my calculator, the third root is, let's see, 1/3 power. So if I do my power key to the 1/3, it'd be the same thing as the third root. Now your calculator might have a root key. Might have the root sign, and then it'll have an X in here, or maybe it'll have something like that. Find it?
Yeah.
Okay, so yours is built in. You just have to know how to use it.
Mhm.
Okay. So you may want to try this also. I got, dividing 4 into this one, I got 7.5 times 10 to the minus 28. So try taking the third root of that. See if you get third root. I'll do the same thing in mine. Let's see. There it is. And see if you get the same answer. So round it off. And we're taking the third root of this one.
Yeah, it's, I got the same thing.
You got the same thing?
Yeah.
Good, okay. All right, so now we can do the more difficult ones. The 27s to the 4th power. So let's do this one. 1.8 exponent 18 to the minus, okay, that one. And we're going to divide by 27. Then I'm going to take the 4th root. And I get 1.6 times 10 to the minus 5. Okay, all right. So now this one, we divided this one by 27. 2x1 33 minus, okay, divided by 27. And then take the 4th root of that. I get yeah. Okay. Now we have to do all that so we can answer the question: which one has the lowest solubility? So I look at the exponents first. Minus 33, 28. This one right here. Lowest solubility. And it's the wrong answer. Okay. Oh. This is a bad day. Line 14. That's the lowest solubility. Right. And if we just go by these numbers, you get the wrong answer like I put up there first. If you just try to use these. You have to calculate the solubility and find out that this one is the lowest, the least soluble cadmium sulfate. The worst part of all that is it's recorded. Any questions? Okay. There should be one in there where you have the same number of ions produced from each one. In that case, you can go ahead and compare the KSPs. Because you could go through all these calculations, but they'd be the same calculation for each one. And would give you the same relative position of each one if they had the same number of ions produced. Okay, that was 11. Thirteen. I need to scroll that. Let's see if this one's different. Ah, it is different. 13. Okay. Now, that was solubility in pure water. The KSP for aqueous solutions for these solids is the same no matter what else is in the solution with it. The KSP is constant for aqueous. The solvent is all that matters relative to the solid that you're trying to dissolve. But common ions can influence the solubility, whereas the KSP is constant. The solubility will change if there are common ions already in solution. Okay, so here's the approach that we make with that one. Barium carbonate, did this one before, makes barium ions plus carbonate ions. Okay. So this one does need a nice table. Okay. The question is what? Molar solubility. All right. So we want to know what is S for this thing. So when we start off, we're really only interested in name anyway for equilibrium. So when we start off, how much carbonate do we have in solution? Nothing. No carbonate. But we do have 0.1 molar barium ion. Because this goes completely into solution. This chloride of barium goes into solution. So we're starting off with 0.1 molar barium ions initially. Okay? So, since there are no carbonates, which way is this one going to move, according to Le Chatelier? That way. So we're going to produce some carbonate, and for however much this goes into solution, we get one of those carbonates, 1 to 1. We also get, if one of these goes in, we get one of these. So now we can write the equilibrium, which is 0.1 plus S, and this is S. So that's where you start your equilibrium expression, which 1.6 times 10 to the minus 9 equals 0.1 times the plus. There we go. Okay. So if we try to resolve this one, we're going to get an S squared and an S and a constant, which means we've got a quadratic. So you can either solve it quadratic, or you can say this amount is going to be very small. I mean, it's going to be very small even if it were pure water. But compared to this value, this is going to be vanishingly small. So we can say, I think very confidently, that we've got 0.10 S. In other words, that one times S is equal to this. So S would just be, let's see, 0.1 over here would be divided by 0.1 or times 10. 1.6 times 10 to the minus 8. Molar. Let's see. Is that what this one says? E. None of these. Right. None of those. Because I say 1.6 times 10 to the minus 8. What does the work problem say?
1.6 times 10 to the negative 8.
Okay. Now we can go in and test, do the 5% rule. So all we would have to do is put this value in here and here, calculate that value and compare it to this one. But it's going to come out less than 5%. I'm confident. All right. How about, let's skip down. We've got some more of these subsequent ones were common ion effects. Okay, 17. Yeah, scroll out. All right, which of the following solid salts is more soluble in 1 molar acid, H+, than in pure water? Okay. Remember, you've got two ways to make a slightly soluble salt more soluble. One way is acidify, right? Add hydrogen ions, or complex ion. So under what circumstances do we do that? For the acidification process, we look for the anion. Look for the anion of the compound. So we've got what? Sodium chloride. We've got calcium carbonate. We've got ACl. We've got silver chloride. And we've got E. Acid nitrate. Okay. If you're going to add hydrogen ions, what you need is a very strong base in the anion position. So if you look at what did this come from? If it were coming from an acid, it would come from hydrochloric acid. Strong acid, weak base. So this one's weak. All these chlorides would be weak. Nitrate, nitric acid is strong too. So that makes it a weak base. So the only one that works is the carbonate. Now, why is that? Why does the carbonate become more soluble in acidic solution? Well, when we write out the equation, Okay. But I'm going to leave out the aqueous parts. This is slightly soluble, but if you add hydrogen ions, they're going to react with this strong base. A strong base wants hydrogen ions really bad. So if you put hydrogen ions in here, what's it going to do? It's going to make the hydrogen carbonate ion. And more than likely, it will pick up another one and make carbonic acid. Okay? So what that's doing is it's removing this one from that side of the reaction. Right? And when it does that, we invoke Le Chatelier. We take away this product, it moves the reaction that direction, solubilizes milk calcium carbonate. Actually, it does make this, and then this decomposes. Actually, it makes carbon dioxide and water. So if you add acid calcium carbonate, you're going to get a fizz. It's going to make carbon dioxide gas, which is even better, right? Because now the carbonate has gone all the way through this process and it's completely removed from the reaction environment. There's no way to get it back. Okay, so that's why B is the answer to number 17. Now, if you're trying to solubilize, I think one of our examples here was silver chloride. Acidification won't work because that's a weak base. So we have to approach the cation to get this one in solution. So if it's going to make silver ions plus chloride ions, then we need something that will remove this from that reaction equation. And to do that, we add ammonia. Actually, 2 of them. And that makes this complex ion. Okay? That's the one we would have done last week, I think, or the week before. Only we're here, right? It's not scared quick by jumping the gun. Complex ion. Oh no, we are going to do that. It's coming up. We're going to do the Ka for acetic acid today, right? I do have that right.
No. We did that when we weren't here.
Oh, so we are going to do the complex ion today.
Yeah.
Okay, so I got ready for the wrong lab. I'm going to have to fix that before we go in there. Actually, the complex ion is more fun anyway. Okay, I just don't want to eat up all our time. It's already 9 o'clock. Let's see how much more time I've got. 10:50. I'll probably finish by 10:15 if I can. That'll give us a little more time.
Right into the bathroom.
Okay. Let's see, set up for the next one. Nope, too far. This is 19. You have a solution consisting of 0.1 molar chloride, 0.1 molar chromate. You add 0.1 molar silver nitrate dropwise to this solution. Okay. Which one of these compounds precipitates first? So we've got two possible reactions happening here. Molar chloride, correct? And this one is 0.1 molar chromate. Okay? So two possibilities. If we've got silver nitrate in solution, nitrate's going to be a spectator. We're only interested in the silver, right? So in this case, silver plus chloride yields this one. That's the solubility we want to investigate here. This one, we want silver chromate solid, and it's going to yield silver chromate. Okay, and we're given the KSPs for each one, yeah. KSP for silver chloride is 1.6 times 10 to the minus 10. And KSP for this one is 9 times 10 to the minus 12. 9 times 10 to the minus 12. Now, first off, I wrote this one wrong. That's a 2. Because this is a 2 minus, we need 2 of these. There we go. Okay, which one's going to precipitate first? The one with the lowest solubility will precipitate first. So what is the solubility of each one? Well, this one, if the solubility of this one is S, then this one's going to be S, and this one's going to be S. So this is equal to S squared, correct? That means S is the square root of that value. So at 1.6 and the minus 10, and we're going to take the square root of that. 1.3 times 10 to the minus 5. Okay. And this one is going to be, this is S, this would be 2S, and this would be S. So this would be equal to 2S squared and S, which would be equal to 4S to the third. So we divide 4 into this one and take the cube root of it. 9 exponent to minus 12. And then divide by 4. Take the cube root. So I get solubility is equal to 1.3 times 10 to the minus 4. Okay? So in order to determine which one precipitates first, we need to know what the solubility is. And the solubility of silver chloride is an order of magnitude less than the solubility of silver chromate. So that's why, let's see, A. That's why A is the answer. Okay, and we can't answer that question unless we determine the solubilities of each one. All right, that was 19. Let's see. I got 21 marked, but I've identified that one as difficult. So let's save 21. I'll come back to it. Let's get the easy ones out of the way. 23. There we go. A solution of 0.01 molar of lead nitrate, manganese nitrate, zinc nitrate. Oh, each, 0.01 molar each. Solid sodium hydroxide is added until the pH of the solution is 8.5. Which of the following statements is true? Note with strip the table form, only this one. Okay. Okay. Each one of these salts is the same number of ions. So we're looking at solubility. Actually, the solubility comparison is lead, manganese, zinc, and each one has 2 hydroxides. Now, why is that? That's because we added sodium hydroxide. Right? And the hydroxides of each one of these are nominally insoluble, but they have a limited solubility based on these values. So since we produce 3 ions each, we can directly compare their K values. Right? This one has lead hydroxide, has the least solubility. Zinc has the next least. Manganese hydroxide is most soluble of all these 3. The question, though, is not just which is more soluble, but which is more soluble under these conditions. Okay. So we need to compare. And if we just write one of them out, then we can get an idea. So the solubility, and S is the solubility for each one of these, then the term is going to be S here, 2S here, and the KSP for each one is going to be 4S cubed. But if we write this in those terms, actually, this is for pure water. Well, we don't have pure water anymore. We have a very strong base, OH minus. So we've modified the system. All right, so forget that. Let's just do this one first. Initial change, equilibrium. All right. Initially, how much lead do we have here? 0.01. 0.01. Okay. And before we do anything, we have no hydroxyls. So actually, no, that's not right. We do have hydroxyls. But how many hydroxyls? 8.5 pH. Okay? So what's the POH? 14 minus that, right? 5.5 is the POH. 14 minus 8.5. 14 minus 8 is 6. So another half would drop it down to 5.5, right? Okay, so now we can calculate the OH concentration. We just need negative log, excuse me, that's not right, 10 to the minus 5.5. That's the OH concentration. So I get 3.16 times 10 to the minus 6. Molar. And this is OH. Okay. Now we start off with 3.16 times 10 to the minus 6 molar. I'm making this more complicated than it needs to be. Just get that feeling. All right. Yeah, I'm going a long way around the barn. What we need is, we do need that value, 3.16 times 10 minus 6. And I'm going to leave that down there. So for this one, the KSP is equal to what? 1.4 times 10 to the minus 20. For this one, KSP is 2 times 10 to the minus 13. And for zinc, KSP equals 2.1 times 10 to the minus 16. Okay, in order to determine which way is the reaction going to go, right? If you have this much in solution and you've got so much of this in solution, you want to see, does this come out of solution? So what we're actually comparing is the KSPs and the Qs. So if the Q value is greater than the KSP, then it's going to shift back this way, because that means you have too much product, correct? So if we're expecting precipitation, the Q has to be greater than the KSP. And that would answer the question. All right, we've already got this value here. So what's the Q for this one? Well, Q for this one is going to be, let's see, what is that? 0.01 for the lead, 0.01 for the lead, and then 3.16 times 10 to the minus 6 squared. And actually, the Q is going to be the same for each one, isn't it? That stuff. There it is. No, that's not it. 23. There it is. Right. The Q for each one is going to be the same because the environment has so much hydroxyl in it. Right? We calculated that value right here. And the concentrations of the ions are the same value, 0.01 molar. So if we calculate the Q, we can compare that to each one. So what is the Q? Well, we'll have to calculate it. 3.16 exponent 6, and then we're going to square that one, and then times 0.01. So that's 1 times 10 to the minus 13. Rounded off. Actually, it's 9.9856 times 10 to the minus 14. You round that up to 10, that brings it down to 1 times 10 to the minus 13. So we compare each one of them to this value. So this is less than Q. It won't precipitate. This is greater than Q, right? Twice as high. And this one is less than Q, right? Yeah. So the only one that's going to precipitate is manganese hydroxide. Wait a minute. Have I got that backwards? What's that? If the Q is greater than that's KSP greater than Q. I was right the first time, I just read it wrong. The KSP is less than Q. Q is greater than KSP, that will precipitate, which means lead and zinc will precipitate. That's what. Okay. Did I thoroughly confuse you? It's the moral of this story is, once you've determined, you're given these amounts right here for the ions, 0.01 molar. We just had to determine what's OH because the precipitation is based upon what is the hydroxyl concentration. And if you can find out what that is, then you can calculate the Q for each reaction. And actually, the Q is the same for each reaction because the hydroxyl is the same, the concentration of the ions is the same. All we have to do is calculate the Q and compare it to the K. And if the Q is greater than K, that means we've got too much of this, which means it's going to precipitate. Okay, that's the moral of that story. All right, 23. Let's see if I can do 24 without messing it up. Hmm. 24 doesn't have a description, does it? Mm-hmm. Okay. Well, that's all more reason to do it. Okay, in the qualitative analysis scheme for metal ions, how are the analytical group 2 cations separated from? Oh, all you have to do is look at the useful information. It's there. I put that scheme in here. Separation scheme. There it is. How are the analytical group 2 cations separated? Okay, analytical group 2. So these are the ones. The ones are silver chloride, mercury 1 chloride, and lead 2 chloride. That's group 1. Those are separated by acidifying. Then if you add hydrogen sulfide, add hydrogen sulfide to the acidic solution, we form the insoluble metal sulfide. You remember that discussion in class? Why does acidic solution precipitate the lesser soluble ones? Because in order to solubilize the lesser soluble ones, we need to reduce this amount considerably in order to pull out the group 2s, copper, bismuth, cadmium, lead, mercury 2, arsenic, antimony, tin. In order to get those out, we need to have this low value so it doesn't precipitate out the more soluble group 3s. So if we add hydrogen ions, acidify the solution, it drives the reaction back this way and decreases that concentration. So now we can pull out the lesser soluble sulfides. Then if we add the base, we can pull out the more soluble sulfides, because if we add the base, that makes water, and that drives this reaction to sulfide. It makes more sulfide. Okay, so that's why I didn't put an explanation, because all you had to do was just look at the chart. From board. Okay. 25. Which of the following solid salts should be more soluble in liquid? Oh, okay. This one should be fairly simple. 25. This is the other way to solubilize insoluble salts. Which of the following solid salts should be more soluble in 1 molar ammonia? So in this environment, we're asking which ones of these salts would be more soluble. Na2CO3, HCl, silver bromide, KNO3, and none. Okay, so if we were to approach this from acidify the solution, we would look for the strong base, which would be this one. But if we're going to approach it from the cation end, we need to form a complex ion. Which one of these forms a complex ion with sodium? Sodium doesn't. I mean, with ammonia, excuse me. Sodium doesn't. Potassium doesn't. Silver does. And silver bromide is very insoluble. So that's why C is the answer. It's really simple, actually. In fact, that's the only one we studied that makes a complex ion with ammonia. There are several others. Let's see, did I put those in here? Formation constants? Yeah. Okay. There's silver in ammonia. Let's see if there are any other ammonias in here. There's a cobalt in ammonia. Actually, 2 of them. There's a copper in ammonia. There's a nickel in ammonia and a zinc in ammonia. So you could form complex ions with any one of those and increase their solubility if they were combined with an anion that decreased their solubility. Okay. 26. No, 25. Yeah, 25. 27. And you could go down. There it is. Correct mathematical expression for the solubility of barium chloride. Right. This just to see if you remember what we discussed earlier. Got to write barium chloride correctly, right? It's not given to us. Barium chloride. Is that insoluble? Barium chloride? I thought all the chlorides were soluble, except for just a couple. In the solubility table. Is it in here? No, it's not. Oh, we got KSPs. Chlorides. I don't know about that one. I thought barium chloride was completely soluble. For argument's sake, what would it be? Okay. So if this is S, that's S, and this is 2S. So it would be S times 2S squared, which would be 4S cubed. Right. That would be the KSP for this one. Although I still think barium chloride is completely soluble. I have to check. Then I don't think I had that solubility chart. Okay, 30. 30, 27. Yeah, 30. There it is. Which of the following leads to the formation of precipitate? All right, this is just memorized. If the Q is greater than the KSP, you will get a precipitate. That's why it's only worth 1 point here. Well, actually, that's 1 point. Okay, that's right. Yeah, that's right. I'm just comparing that with this one. Okay, I'm going to skip 34, come back to it. That's a difficult one. I'm going to get all the easy ones first. At 36. And scroll that one. Okay. And calcium fluoride is an insoluble salt. So calcium fluoride, how many moles of calcium fluoride will dissolve in 3 liters of 0.089 molar sodium fluoride solution? So our KSP is based upon this reaction. Okay? But we have a common ion. So we want to find out what's the solubility here under those conditions. So we've got sodium fluoride. We have no calcium in solution initially, but we do start off with 0.089 molar fluoride, right? Because sodium fluoride breaks into, this molarity of sodium fluoride breaks into 0.089 molar fluoride ions. So that's what we're starting with. But since we have none of this, the reaction is going to move that way. And it's going to take with it this many. And 2 of those. All right? So our equilibrium expression is this. 2S plus 0.089. That means our KSP is equal to what value 4 times 10 to the minus 11. Is equal to S and 2S plus 0.089 squared. All right. Can we simplify this? Well, let me see. This is going to be pretty small to begin with. Is it small in comparison to that number? That's the question. 10 to the minus 11. What would be the solubility without this stuff? It would be 4s cubed, right? So 4s cubed, based upon this, I'll just do a quick calculation. What would be the solubility without the common ion? Did I do that right? 4s cubed. So I'm going to divide this number by 4 and then take the cube root of it. Oh, that was wrong. Let's try it again. And then take the cube root. So it's about 2 times 10 to the minus 4. 2 times 10 to the minus 4. This is minus 2. Yeah. I think this would be much, much smaller than that. So what we can do is we can say this is approximately equal to S. This is 0.089 squared. So if we square 0.089, and then divide it into 4 times 10 to the minus 11, and I get 5 times 10 to the minus 9 equals S. Let's see, 36. 1.5 times 10 to the minus 8. Okay, what did I do wrong? Oh, that's the solubility. That doesn't answer the question, right? How many moles of calcium fluoride will dissolve? I didn't even read my own question. That's the molarity. So molarity times volume equals moles. So 3 times that. Is 1.5 times 10 to the minus 8 moles. That's what he answers. I'm not having a good day today. Okay, 37. This is a logical question. What's the best way to ensure complete precipitation of this? S and S. from a saturated H2S, from a saturated H2S solution? Well, you're going to get some precipitation anyway, because you've got some sulfide ions in there. This is a solid. Right. You're going to get some 10,2 sulfide out of that solution because it's saturated with H2S. But you want to be sure you get all of it, right? So you need this value to be as high as you can get it. So how do you make that as high as you can get it out of this? Right? You add a strong base. If you have a strong base of any kind, just take your pick. OH minus is extremely strong. Then you get water here, and you actually drive. That's not solid, that's in solution. You actually drive this reaction to make as much of this as possible. And if you can increase this, you can increase that and drive the reaction back to that. Okay? That thing putting you to sleep. Okay, 37. Let's look at Forty-one. Okay. We've got a solution with 0.018 moles each of iodine, bromine, and chloride. Iodine, bromide, chloride. When the solution is mixed with 200 milliliters, 0.24 molar silver nitrate, how much silver chloride precipitates out? All right, so let's see. What are we given first? We're given 0.018 moles of iodine, bromide, and chloride. That's given each. Okay, we're going to mix that solution with 200 milliliters of 0.24 molar silver nitrate. Okay, and the question is, how much silver chloride precipitates? Oh, that's the question. And we look, our answers are in grams. Okay. So what we want to do is first compare the KSPs for each one. So silver iodide, let's see. Silver iodide, KSP is 10 to the minus 16. Silver bromide is 10 to the minus 13. And silver chloride, KSP, is 10 to the minus 10. Okay, first thing to notice is we've got the same number of ions from each one, which means we can directly compare these and say which one comes out first. Okay? Silver iodide is going to precipitate first. So, how many moles of silver do we start with? We start with 0.24 times 0.2 liters. That gives you how many moles of silver. So 0.2 liters times 0.24 molar equals what? Let's see. 0.048 moles of silver to start with. All right. So if this one's going to precipitate first, and it's going to take all the iodide out of solution, you've got 0.018 moles of iodide and 0.048 moles of silver, and they're 1 to 1. So 0.048 moles of silver. And then we're going to subtract 0.018 moles of silver required to make iodide. Okay, so that means we have what? 030 moles. That's what we got left after iodide's gone. Next, bromide. So bromide is 0.018. And the only reason I can do this is because they're 1 to 1. So the amount of silver is equal to the amount of silver bromide that we can extract from that. 0.012, right? That's what silver we have left. Okay? So even though we have 0.018 mole of chloride, we can only, the silver is limiting. If it were 1 to 1, if it was stoichiometric, then we could make that much, but we can't. We can only make this much. So that's how many moles of silver we can precipitate as silver chloride. All right? So how much silver chloride precipitates? Well, these are 1 to 1, so 0.012 moles of silver chloride. Now we just need to find out what's the molar mass of silver chloride. Doesn't tell us, does it? Okay. Silver, 107.87. Right? Chloride, get that one memorized. 3545. Okay. So I get 143.32. So did we do that? Yeah, cancel moles of these grams. 0.012 is 1.7 grams of silver chloride precipitate. There it is. Okay. I need to get at least one more. Fumbling around. All right, that was 41. Do it on time. Okay. See how many I can get done in the next half hour. Oh, 43. 43 is just, look at your chart again. When a mixture containing cations of analytical groups 1 through 3 is treated with H2S in acidic solution, which cations are expected to precipitate? On group 2, group 1 and 2. If you're treating all 3 of these together, all 3 groups together, and the solution is not just acidic, but H2S, then you're going to get the first 2 groups pulled out at the same time. That may not be desirable for an analytical step, but for a theoretical situation, that's what will happen. You may not want it, but you're going to get it. If you acidify the solution with H2S, then you're going to get both of these groups out. But actually, it's not just acidify the solution. You have to add hydrochloric acid to acidify it, because you're going to get the chlorides out of group 1. So that should be more specific. H2S in hydrochloric acid solution. That would be accurate. 43, 46. Oops, 46. Let me scroll right here. Okay. I know where this one's going. 46. The cation M2 plus reacts with NH3. M2 plus reacts with ammonia. In this series of complex ions. So it picks up one ammonia, makes that with this K value. Then it picks up another one with this K value. It picks up another one with this K value. So a 1 times 10 to the minus third mole sample of MnO3 is added to 1 liter of 15 molar ammonia. KB this. Choose the dominant species in this solution. That information right there for this problem is blue smoke. You don't need that. All you need to know is that there's plenty of ammonia there. So where is it going to go? Well, the first reaction, right, is going to take it to MnH3 2 plus. But look at the K value, 10 squared. It's all over here. Then you're going to take that and add another ammonia. Where is it going to be? It's going to be all over here too. So it's going to take whatever here and convert it completely to the next one. And then the third one is going to take all of that and convert it to this. So the dominant species in that solution is the final one here. Based upon these choices, right? NH3 sub 3 2 plus. Now, if I were going to be mean, if I'm going to be evil, one of my selections would be ammonia. Which was the dominant species in there? It's ammonia. I mean, you use up all of this, but you still got lots of ammonia left over. Okay, so beware. I'm not that evil, but if some instructor in the future decides to give you the question like this, then that's the trick. Ammonia is still the dominant species in there, but that's not one of our selections. The focus here is on the ammonia complexes, and to recognize that the equilibrium expression here goes all the way down here. In fact, you can do a composite. Just add these together, and then the K's you multiply, correct? If you add the reactions together, you multiply the K's. So if we say 10 squared times 10 to the third times 10 would be 2, 4, 7. 10 to the 7th would be the equilibrium expression for this all the way down to that. So that's another way to look at it. Now, if we had, say, one of these, say this one right here, was 10 to the minus 3. The dominant species would be that one. Okay? But that rarely happens when we're making complex ions. Okay, 46. $47. What's the concentration of nickel? 2 plus in a 0.045 nickel nitrate solution that is also 1 molar ammonia. And the Kf for this compound here is 5 times 10 to the 8. Okay. 47? Yeah, 47. This type of problem is best approached in 2 stages. First, the stoichiometry, and then the equilibrium. So the controlling equation here is nickel 2 plus, nickel 2 plus, and this is aqueous, and ammonia, aqueous. But there are 6 of them. Right? 6 of them right here. Yields nickel and ammonia. 6 of them. Still has its charge though, because ammonia is neutral. And the Kf for this equation is, sure. Yeah, Kf for this equation is 5 times 10 to the 8. Okay, so what we're looking for is what's the concentration of nickel ion in 0.045 molar nickel nitrate. So if we're starting off with 0.045 molar nickel nitrate. 1 nickel, that's 2 plus nickel. There we go. And 1 molar ammonia. Okay, so we do the stoichiometry first. And I think I want to approach this the same way I would. Okay. So let's do the stoichiometry for this one. What's the nickel ion concentration to start with? It's 0.045 molar. That's nickel. And the ammonia concentration is 1.0 molar. Okay. Yes. Okay. Stoichiometry says that we're going to, the limiting reactant is this one. I think. Let's see, 6 times this would be what? 4 is 27 to 0.27, right? 33 and 14, yeah. So that means we need this much ammonia to complex with all of the nickel. Right? So if we do that, that means that we start off with 0 here. And this is initial. And this is final. That's 0. And this is minus 2, 1, minus, what did I say, 0.270? Yeah. Okay. And what do we get over here? Well, now we have 0.045 molar because it's 1 to 1, 1 to 1. Okay. So this is the stoichiometry. This is the stoichiometry part right here. Now, this is where our equilibrium starts. So if we do the equilibrium, we have our ice table. And this is our initial position. And what is that? Right? Yeah. And this is 0. So that's where we start for equilibrium. If we try to do equilibrium first, it just wouldn't work. Because we don't know our starting position. This is really not a starting position for an equilibrium, right? So since we've got none of this, some of it's going to move back this direction, right? So we're going to have some, let me go back to the question. What's the concentration of nickel ion in solution? So this is what we're looking for, this change. How much of that now is in solution? But it's important to pick your unknowns. If we solve for this, we'll answer the question. All right? So if you have this one, where did it come from? Well, it came from here over here. Right? And it's 1 to 1, so it's minus x for that. And over here, it's plus 6x. Because 6 of these for every 1 of those makes that. Okay? So now our equilibrium expression would be this one. It would be 0.73 plus 6x. And this one would be 0.045 minus x. So our equilibrium expression with this formation constant, well, there it is right there, is 5.5 times 10 to the 8th equals this one, 0.045 minus x to the first power divided by x here to the first power times 0.7306x to the 6th power. Good luck solving that one. Let's see, can I simplify it? Okay, we're going to make an assumption here. Compared to what? Let's see, which one can we eliminate? We're going to say that this x compared to these values is going to be very small. That X is small compared to this one, that X is small compared to this one. So this is approximately 0.045 divided by X times 0.730 to the 6th power. And then we're going to solve for that X. And that should give us 5.4 times 10 to the minus 10. Now, in order to verify that, we would have to plug this value in here, 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 calculate that, and compare it to this one. But we can also look and see, are we justified? 10 to the minus 10. This is 10 to the minus 2. And this is 10 to the minus 1. So I think we're justified. 10 to the minus 10. Yeah. I think we're justified in making that approximation. If this had come out to my 10 to the minus 1, we'd have to do successive approximations because I don't know the formula for the 6th root. For the, what would that be? Let's see. Linear, quadratic, cubic, quartic. What's 5? Pentic. I don't know. Hexic. Maybe there is one, a solution like our quadratic equation, a solution for the 6th, but I don't know what it is. So we'd have to use successive approximations to do that. It could be done. I just wouldn't want to have to do it on a test because it'd take a while. All right. That was 47. Let's see. We want to do 50. The KF for the complex ion here, the one we're using today, is 1.7 times 10 to the 7. That would be our accepted value, the one we would compare the results of our work today. KSP for silver chloride is this value. Calculate the molar solubility of silver chloride in 1 molar ammonia. All right. The only reason I want to tackle this one is because it has a direct bearing on our approach today. Let's see. Okay. All right. This would be a good one. What are the two equations? Remember, both of these reactions are going on at the same time in that solution, where we're forming the complex ion and precipitation of silver chloride. So both of them are happening at exactly the same time. And this is the formation constant equation. There. And that one has a KF of 1.7 times 10 to the 7. I think I've seen 1.8 also. In fact, their method may have 1.8 as our accepted value. Then the solubility of silver chloride, solid, silver ions, and chloride ions.
And the K, SP for this one is 1.6 times 10 minus 10. Okay? So, can we combine these equations? All right, what do they have in common? Well, if we just add these two equations together, because what's going to happen is we want to find out the solubility of silver chloride, correct? The molar solubility of silver chloride. So we want to keep it in this order because that's the direction we want to go. And this is a competing reaction. So if we combine these two reactions, what do we get? Well, we get the silvers are going to cancel. Right? So we're going to get silver chloride solid plus 2 ammonia yield silver ammonia complex plus chloride ions. Correct? Okay. So the K for this expression, let's see, make sure I'm not parking at the wrong tree. Yeah. So the K for this equation is equal to the silver ammonia complex, one of those, times the chlorides, divided by, oops, that's a solid, doesn't count. Squared. And what's the value for that one? This one times that one. So 1.7 exponent 7, 1.6 exponent 10. Change that. So I get 2.72. I'm going to hang on to some decimals here. 2.72 times 10 to the minus 3. Okay. We're after the solubility of we're after the solubility of silver chloride. Now, there's no silver chloride in that expression, but for every 1 silver chloride, we make 1 chloride, and we make 1 ammonia, right? So the unknown here, that solubility is there. So what about this one? What is that one equal to? Should be 2s. Well, no, actually, it's the starting point here is whatever this is, this produces, combines this, so that's 2s. So whatever this happens to start from is what? 1 molar? Right, 1 molar. 1 molar. It's going to be minus 2s. That's what's left over because we're using 2 of them. Right, for every one of these, you need 2 of those. So that's our equilibrium position. Let's see, that's not S. That's 1 minus 2s. This is S. And ammonia no, that's not right. I had it right the first time. because you've got one silver in here. This is S. And this started off at that. And then we're subtracting 1 minus 2S to get this, 1 minus 2S. Okay. So there's our expression. This one times this one squared equals that value. And now we just solve for S. So that's S squared over 1 minus 2S squared equals 2.72 times 10 to the minus 3. Okay, did I lose anybody in that process? Combining the equations gives us the equilibrium situation. And the equilibrium is related to the solubility here by how much silver it produces, how much chloride it produces. So chloride is the only factor we have in here. And we've used the chloride as S, right? One of these makes one of those. But one of these also makes one of those. So that's why this is S and that's S. And this started out at 1 ammonia. And we're subtracting 2 S's from it. So, how do we solve this one? Fortunately, both of these terms are squared. So if we square the whole equation, do I need to square the whole equation? I think you do. So square root, excuse me. Take the square root of the whole thing. So the square root of this is S over 1 minus 2S. And that's equal to the square root of 2.72 times 10 to the minus 3. Now it's simple. Just take the square root of that and solve for S. And S should be 4.7 times 10 to the minus 2. Molar solubility of silver chloride in 1 molar ammonia. Okay? Sort of. We're going to use a similar approach today. But instead of just straight combining the equations, we're going to take the equivalence of one equation and set it equal to the KSP for silver chloride and insert that into the equation. Because we're looking for a solution of what's KF. I did this review last week, didn't I? And then an introduction for the lab. Didn't I do that last week? Yeah. Okay. So it's in Blackboard.